So in this first example, we're going to sketch the graph of a rational function. So we've got 2 plus x minus x squared over x minus 1 all squared. What's the domain of this function? What's the domain? Well, it makes sense to plug in any real number except where the denominator is vanishing. And so our domain here is the set of all real numbers such that x is not equal to 1. So we're excluding 1, and that's the only value we have to exclude on the real number line from our domain. Okay, so what about our intercepts? Do we have any x-intercepts? And do we have any y-intercepts? It's not necessary to work these things out to get to the graph of the function. But of course, when we do plot the function, we're going to see it may intersect some of these axes. And it would be a good thing to identify these places where it intersects the axes, because that's all part of the sketch. So whether we do it now or we do it later, we're going to have to essentially find these intercepts one way or the other. So let's go ahead and start with them now. X-intercepts. Where do those occur? Well, those are where the y value is 0. So where is our function 0? Well, it may help to express our function in a slightly different way. Let's factor the top so we can identify the roots of the numerator easily. So I factored out a negative sign from all the terms, and now I can factor that numerator. It's x minus 2, x plus 1, all over x minus 1 all squared. So where are the x-intercepts? Well, the x-intercepts are where the function is 0, and that's at 2 and negative 1. So x equals 2 and negative 1. So maybe we can identify then the points. Those are the x values. So the points are 2, 0, and negative 1, 0. What about our y-intercepts? Well, our y-intercepts are where x is 0. So we just have to pop x equals 0. We can plug it into either form, the factored form or the original form of f. So we plug in x equals 0, and we get 2 over 1 for 2. So the point is 0, 2. Okay, so we've identified 3 points on the graph of our function. What's next? Well, we can exploit any symmetry if it has any. Just looking at this, we see that there's a mix of even powers of x, odd powers of x. It doesn't look like it has even or odd symmetry. It's a rational function, probably not periodic. In fact, periodicity usually only comes when you're dealing with trig functions, or if the function explicitly is stated as periodic through some sort of piecewise definition. So here, there doesn't look to be like there's any symmetry on this function, so we'll move on to the next one. What's the next stage? Well, the next stage is to look for asymptotes. So we'll look for any horizontal asymptotes. So horizontal asymptotes. Well, those are found by looking at the limit as x goes to positive infinity, and also the limit as x goes to negative infinity. So we look at both directions. What's the end behavior in either direction? Well, this is a rational function, degree 2 over degree 2. So we know we can get the horizontal asymptote, or the limit as we go to positive or negative infinity, by looking at the ratio of the leading coefficients of top and bottom. Coefficient of the leading term up top is negative 1. You'll have to expand the bottom to see its leading term, but it's going to be x times x, or x squared. So we've got a coefficient of 1 in front of that. And so it's negative 1 over 1. And so therefore, it has a horizontal asymptote of value y equals negative 1. And this is also the limit as x goes to negative infinity as well of f of x. So y equals negative 1 is a horizontal asymptote. What about a vertical asymptote? Are there any places where if we take the limit as x goes to that value a, that the function blows up at, either positive or negative infinity? Well, for a rational function, it's going to be these places where potentially the denominator is 0, providing that the numerator isn't also 0 there, in which case there is a hole. So it looks like we have a potential candidate for an asymptote at 1. So what we're going to do is we're going to head to 1 from the left of our function, and then we'll also head towards 1 from the right and see what happens as we approach it from either direction. So that's the limit as x goes to 1 from the left. Now we've got a choice of which form to use. Really the point here is we already know from the factored form that the numerator is not vanishing at 1. 1 is not a root of the numerator, so I can use either the original form or this factored form of my function. Why don't we just go ahead and use the factored form. X minus 1 all squared. So as we head towards 1 from the left, this means our values of x are smaller than 1 and getting closer and closer to 1. So we're always smaller than 1. So what's x minus 2? Well, that's going to be roughly negative 1. What's x plus 1? That's roughly 2. So that's a positive 2. That's a negative 1 plus another negative. So the top is going towards a non-zero positive number. What's our bottom going towards? Well, our bottom's going towards 0, and it's going towards 0, and since it's squared, it's going towards 0 through positive numbers. So we've got a non-zero positive over a really small positive getting close to 0. So this whole thing is going to infinity, positive infinity. So this is a non-zero positive number, and this thing is heading towards 0 from the right. That's really how we conclude this. Okay, it's going towards a non-zero positive. I'm going to erase that because in particular this was going towards 2 times 1, negative 1 times negative 1, so it's heading towards 2. So this limit is heading towards something like 2 over something getting close to 0 through positive values, so the ratio is going to infinity. What about the next one? Well, here we're going to 1 through values slightly bigger than 1. Nothing really changes in this argument. The numerator is still going towards 2. The denominator is still going towards 0 through positive values because we're squaring it. So this is still going towards infinity. So we have a vertical asymptote. So we've got x equals 1 is a vertical asymptote. And we know exactly what the behavior here is. It's heading towards infinity no matter what side you approach 1 at. All right, so we're making some progress. We've got some asymptotes. What's next? Well, now we need to figure out where the function is increasing, where it's decreasing, any local extrema. So we'll go ahead and look for our intervals of increase and decrease. How do we get those? Well, we look at the derivative. So what is f prime of x? Now I'm going to spare the details of working out the derivative in full detail here because this is now an exercise in differentiation. I'm more interested in doing this example for what we can figure out once we have the derivative. So once we compute the derivative, we get that the value is x minus 5 all over x minus 1 cubed. So use the quotient rule and you go through all the algebra, and this is what it will simplify down to. So what do we have? Well, we need to find our critical numbers. Remember, we're interested in figuring out where the function is increasing and decreasing. That's where the derivative is positive or negative. And to figure out where it's positive or negative, we first look to see where it's 0 or undefined, and then we look on the intervals between those special values, those critical numbers, to figure out what the sign is on those intervals. So we look for our critical numbers. Where is it 0? So it is 0 when the numerator is 0 in this case. So that's x equals 5. We also know that the function's undefined at 1. That's not a critical number, though. Remember, a critical number's got to be in the domain. And we already know that 1 isn't in the domain. However, we still do want to consider it because there could be a sign change. As we pass over that value that's not in the domain, the derivative could change sign. So let's go ahead and work out a sign chart. So I'll draw a horizontal real number line here. We've got, I use a little x to denote that this number is not in the domain. That's our 1. We've got our other critical number here, well, our only critical number, is 5, and I want to know what is the sign of our derivative. What is it? Okay, so when we're to the left of 1, what is our sign? Well, pick a test point here. So let's say 0. Then the denominator is negative, the numerator is negative, so the whole thing is positive. What about between 1 and 5? Again, we can pick a test point. Let's say 2. The numerator, 2 minus 5, that would be negative. 2 minus 1, that's positive, so negative over positive, that's negative. And beyond 5, both the numerator and denominator are positive. So there's our signs. Our derivative goes positive, negative, positive. What does that mean for our function? It means that it's increasing, decreasing, then increasing. So we have that f is increasing on the interval from negative infinity to 1 and also from 5 to infinity. And f is decreasing on the interval from 1 to 5. We see also that 5, this critical number here, is a local min. So we have a local min which occurs at 5 and has a value of -9/8, which you just get by taking 5 and plugging it into our original function, our original expression. Plug it in for the f up here, and you'll get that your local minimum value is -9/8. Okay, so we found our increase and decrease intervals. We've also got our local extrema. Let's go ahead and look at concavity now. So where's the concave up and where's the concave down? Well, for that we need our second derivative. So we can take our first derivative here and go ahead and differentiate using the quotient rule, and we can get our second derivative. And our second derivative turns out to be -2 times x minus 7 all over x minus 1 to the 4th. So you use the quotient rule, and then a little bit of simplification gets you down to this. Okay, and we play pretty much the same game we just did for our intervals of increase and decrease. We look to see where the second derivative is 0, because those are the potential places where we get a sign change, and then we look at what the sign is on the intervals between those values, and of course the value 1 as well, because it's not in the domain, so we could get a sign change on the second derivative there. 2. So where is our second derivative 0? Well, our second derivative is 0 when x is equal to 7. So let's go ahead and do our sign chart. 1 is not in the domain. 7 is a potential place where we get a sign change. What is the sign of our second derivative? Well, if I pick a value to the left of 1, let's say 0, and plug it in, the numerator is negative, negative. Notice the denominator is always positive because of that 4th power there. It's an even power of the bottom. So when I plug 0 in, I get a negative times a negative up top, so a positive over a positive, that's positive. Between 1 and 7, let's pick 2. Then I get negative, negative again over a positive, so that's still positive. And then from 7 onwards, my numerator becomes negative, because I get a -2 times something bigger than 0, because x is bigger than 7 now, so x minus 7 is positive. So -2 times a positive, that's a negative number divided by a positive, that's still negative. So f is concave up, concave up, concave down. And so let's just jot this down. F is concave up on the interval negative infinity to 1, union 1 to 7, and f is concave down on the interval from 7 to infinity. Do we have an inflection point? Well, notice there's a change in concavity at 7. It goes from concave up to concave down. So f has an inflection point at x equals 7, and if we plug 7 back into our original function, we get a value of -40 over 36. Okay, so there's our inflection point. Now we've got all the information we need to sketch the graph. So I'm going to take this, and I'm just going to go to a fresh page to start getting the graph of the function here. Before I start sketching the graph, I'm going to summarize, though, what our sign charts tell us. So we had 1, 5, and 7 were the points where interesting stuff happened. We see that it was increasing, decreasing, increasing on the intervals to 1 and then to 5. So we've got increasing, decreasing, and then increasing beyond 5. So this is all stuff to do with f. Okay, I'm just translating what we found about f. What else do we know about f? Well, I know it's concave up, and it's not until after 7 that it switches to concave down. So it's concave up, concave up, concave up, and then after 7 it switches to concave down. So let's go ahead and put all of that into our sketch. We also had, I need to figure out where to draw that horizontal line. Where's the bulk of my graph going to sit? And we see that we got a local min at -9/8. So that's just below -1. I also know that we have a horizontal asymptote of y equals -1. So I need to make sure that I draw my horizontal axes up a little bit so I can fit that horizontal asymptote at -1 there. Okay, now what do we know? Well, we know a few points on it. Let's go back and see what points we know. This is why it's useful to have those x and y intercepts. 2 and 0 and -1 and 0. So we've got a -1 and 0 and a 2 and 0. So if that's going to be 2, I know I have a vertical asymptote at 1. So then those are points on it. And I also know I have 5 and 7. Some special stuff happens there as well. So I've plotted my 2 points. Maybe I'll do the whole graph in red just so we can see what the graph is. So those 2 points are on my graph. I also know that 0, 2 is on my graph. That's my y-intercept. So 0 up here at 2 is on my graph. What else do I know? Well, I know that it's going to do this, right? It's got to head up that way, and it's got to come down that way. Because I know it's heading off to infinity no matter what side I approach 1. So either from the left or the right, it's going to head off to infinity. So I know it's got to do this, way up here. I know that I've got to approach this asymptote as well, off to the left. As I head off towards -infinity, I got to approach the asymptote. Now here's the question. How do I approach the asymptote? Do I do this, or do I do this? How do we figure that out? Well, one quick way to do that is to say, well, suppose it was the bottom one. Suppose I approached -1 from below. What has to happen? Well, I have to pass through this point here. So I'm only going to dot these in because I'm going to erase them. I'd have to pass through that point. And in order to approach the asymptote from the bottom, I'd have to come down, turn around, and then start to approach it. But if I did a turnaround there, I would have picked that up as a critical point. It's a place where the function's turning around. So it would have had to have been a critical point. If I look back up, I see where are my critical points. Well, I only have one critical number, and it occurs at 5. So there's no way the function could have dipped below and then approached the asymptote from below, because I would have had to have detected a critical point there. So no, it's not coming at it from below. So let's get rid of all this stuff. So what that means is it's got to come at it from above. And so what it looks like is it's going to come down here and pass through these 2 points and then head off towards my asymptote. Now what about the other side? Well, I've got to come down. Notice I'm still, 7's way out here, so all this information in my summary above is telling me that as I leave 1, I'm decreasing concave up, And it's not until I hit 5 that I become increasing again. So I'm coming down, down, down. Now, when do I turn around? Well, I know 5 was my local minimum. What was its value? Local minimum was negative 9/8, so that's just a little below 1. So it's somewhere down here to turn around and come back up. So that's our 5, negative 9/8. Okay, so it's coming down, 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 and then it's got to come down to a minimum. I know I'm concave up all the way until I hit 7, so I know I'm still concave up here, decreasing. I hit that point, that's where I switch to increasing, and when I hit 7, I switch to concave down. So at some point I'm going to have to switch to concave down. What's my value where I switch? What's my y value? I want to know if I'm crossing this before I turn concave down, or if I have to turn concave down if the value at 7 is below the horizontal axis. So I look at my value. Value at 7 is negative 40 over 36. That's still below 1. So that's going to be down here somewhere. That's my 7 and negative 40 over 36. So then I switch. I got to get a concavity switch there, so I got to scream down here, and then I switch to concave down, and I'm still increasing. How do I know I still don't cross the horizontal axis before I come back down? Well, if I did, I'd have to come back down and approach the horizontal axis. That would introduce a critical number, but I already know I only have one critical number, and it occurred at 5. Another way to think about this is if I went across and then came back down again, well, I'd have to go from increasing to decreasing. But I know from my summary here that my function increases from 5 onward, so it's always got to be increasing. So I've got to increase up to my horizontal asymptote. And so there's the sketch of our function. And we've done it all by hand. So this is the idea for this section, is to take all that information we learned about how to get what the shape of a graph is from its first and second derivatives and put it all together to get the sketch of the graph. Now, you may be thinking, well, I could have done this with a graphing utility, right? I could just plug the function in here. You can see me pop it in below. And if I hit enter, then I get the graph of the function. Now, the interesting point about what we've done by hand versus what we get from a computer is that we were able to detect a number of things that aren't really apparent from what we get from this graphing utility. And that is, see how the curve comes down here? It's crossing at 2, and then something happens here. It looks like it's approaching a horizontal asymptote. Looks like it's approaching a horizontal asymptote of negative 1. So we could plot that in. We could say, well, let's look at x equals negative 1. Oh, sorry, that's y equals negative 1. And we can see, oh, okay, it dips below before it approaches it from below. Well, at some point then, it's going to dip. Maybe it hits a lowest point possible before turning around. I can go ahead and try to stretch these axes out to see if I could find a spot where it turns around. Just stretching and rescaling starts to let some of the features become a little bit more apparent. So we do see it comes down before it turns around and goes back up. So then there's a question. What's the local minimum there? Where is it occurring? Kind of looks like it's occurring near 5. Is it? And what's its value? Well, those are the kinds of things we actually computed ourselves by hand. So we don't get those values from looking at a graphing utility. We get those by doing the hand calculations. So in an ideal world, what you're going to be doing is both. You're going to be using graphing utilities to get sort of the general overall shape, but then hand computations to be able to hone in on those special points to find their values exactly. And the combination of the two is what gives you your most power. You're able to sketch graphs, both in the sort of most broad form to get the general shape, but also find the exact values of any points you need. All right, so that's it for this example. We're going to go ahead and do one more example, and then we'll look at an example of a slant asymptote.